Okay, so hi everyone, welcome to this new session of the seminar. And today we have the pleasure to hear from Adolfo Cisterna from the Institute of Theoretical Physics at Charles University in Prague. And today's topic is about new exact solutions in general relativity. So as usual, feel free to ask questions during the talk or at the end. And Adolfo, thank you very much for being here and for the talk. So you have the floor.
Okay, thank you very much. So first of all, let me express my gratitude to Professor Ribeiro for inviting me, to Jordan for organizing all the details of my visit and so on. So yeah, the title is very generic and wide, and there's a reason for that is that we have been working two different subjects related with exact solution recently. One of them has been the construction of new vacuum stationary and asymmetric solutions, purely or electro vacuum, no modified gravity, no extra fields. And the other one is we have been working also in the context of dynamical black holes. So in certain strategies to take compact source and to embed them on cosmological spacetime. So this talk, by request of Professor Ribeiro, will discuss both topics. So I will discuss in the first half of the talk new developments in stationary and asymmetric solutions, and in the second half, I will introduce the topic of dynamical sources, of compact sources on dynamical spacetime. So, the first part. So, let me tell you about these new vacuum and electro vacuum solutions in 4D. To do that, let me just motivate why we should take care of exact solutions. Why we have numerics and we can go and solve very difficult problems with numerics. Why do we take care of going with exact solutions? Well, first of all, given any physical theory, exact solution always plays a major role. In Maxwell theory, for example, exact fields as Coulomb, dipole solenoids, and so on provide us a fundamental toolkit to deal with electromagnetism. In quantum mechanics, exact solutions to the Schrödinger equation, which is also linear quantum equations, give us insight into the quantum world. For example, solving the harmonic oscillator, various potential wells and 3D problems, give us some glances into the ideas behind minimum and degenerated energy states, for example. If you go to nonlinear regime, the role of exact solution is actually even more pertinent, as having intuition or grasping intuition in nonlinear system is much more complicated. This is an example of this, what happened in the interplay between fluid mechanics and astrophysics. And even if numerical computations are relevant to solve highly complex system, however, exact solutions always provide a map to actually then follow with the numerics. It will be difficult to imagine to deal with rotating sources numerically without having any info, for example, from the Kerr solution. So here is an example of an exact solution that actually take the role to go and do numerics and study highly complex systems. But now, sorry, I'm going to mess with this. So, but Einstein equations, they are very complex. They represent a set of nonlinear coupled PDEs, and they pose two main problems. The first one is a mathematical challenge that is related with to find as many solutions as there are, or to find a general solution as complete as possible. So this is purely mathematical. And then there is a physical challenge, which is go beyond the low-gas solution of the PDEs and to try to understand the causal structure of the space-time. So have more intuition about what globally represent these solutions. During the last century, and this monograph here, which is like 700 pages book, expressed most of known exact solutions that are in the literature. So this is nice because we have a lot of info, but it's also not so nice for us that are trying to look for new solutions to the theory, because most of them are already contained in this book, and these guys were very smart, not like us, so they really know what they were doing, and they have explored a lot the spectrum of solutions in GR and in the electrovacuum. So therefore, to find exact solutions is actually very complicated. But how do we try to approach this objective? So mathematically, brute force integration doesn't work unless you are dealing with charge. Obviously, the only one you can solve basically very hard. Normally with Kerr is very complicated, so you need to go and use certain techniques. These techniques, which are precisely what I'm going to discuss in the first half an hour of the talk, are solutionation techniques, basically Lyapunov symmetries of the Einstein field equations that allow us to move in between the spectrum of solutions of the theory. I have a solution that I can consider as a C, apply these symmetries, and these symmetries allow me to find new solutions that are highly trivial to be found by direct integration. And physically, how do we tackle the physical challenge? We simply go and study the causal structure of this space-time different techniques we have at hand. Now, it might sound like, okay, we have an algorithm or a trick to simply go and apply Lippoin symmetries and find new solutions, but actually it's not like that, because to find Lippoin symmetries is very difficult, and even though they have been studied, and there are many, to assess the capability of these transformations to find new novel solutions is also very important. So you might have a kind of Lippoin symmetry, but you don't know what to do with it, or you don't know how to interpret the result. So, what is the standard law of black holes in 4D general relativity? So basically, the most general line element that contains black hole in GR in 4D is given by the Blavatsky-Chemielsky family. There is no need to show you the metric, but schematically, it's a space-time that contains all known solutions we know in 4D GR. It can be also extended to electrovacuum, so you can have a Maxwell field, and you can have also cosmological constant. It basically contains the Schwarzschild solution, the Kerr solution, charge generalizations, and generalization with cosmological constant, and two generalizations that are more exotic, which are the NAT solution and the symmetric one. NAT solution is a kind of gravido-electromagnetic monopole solution, and the symmetric is what is known as the space-time describing accelerating black holes. And combinations of all of these black holes, or these, let's say, parameters that describe the solutions, are all contained in this very wide, large family known as the Blavatsky-Chemielsky family, which, by the way, is the most general type B expanding line element you can find in GR. Notice that here there are two boxes, but both are coming from the same line element. It's just that the causal structure is pretty different when you have more spin than NAT parameter, and when you have more NAT than spin parameter. It's the same metric, but there are two different subsets, and from there you can basically killing either the NAT parameter level or the acceleration alpha or the angular momentum A. You go into distinct subcases until you arrive to the Schwarzschild solution. So it has many advantages to be in a type D spacetime, but it also has some restriction for us. So the advantages are that, first of all, they contain a hidden symmetry, they contain a hidden Jano tensor, and this object is very important because it allows separability of geodesic and wave equation. So most of the physics you know about geodesic in Kerr spacetime is actually due to this result. Now, it's not so nice for us because it is unique and doesn't give us a space to go for new geometries. And actually, there is something interesting is that all these solutions you see here, they are sources on top of a conformally flat spacetime. So it's either Minkowski or it's something with cosmological constant. So when we are dealing with type D spacetime, we would like to find new type D geometries. We are forced to have our sources on a conformally flat spacetime. It's a real restriction for us, and it's difficult to circumvent. And second of all, well, there are certain unique properties that are difficult also to circumvent to try to find new solutions. So the question is now, can we go beyond the Blavatsky-Chemielsky family and retain type D? This is very difficult, but has been recently done. I will show you an example soon. And the other question is it possible to construct an algebraically general black hole? So move away from type D with the same level of generality to find rotating, accelerating, NAT, etc., and combination thereof. So to understand that, we need to know more about the Lippoin symmetries, which are basically the techniques that will allow us to construct these new solutions. And Lippoin symmetries in the electrovacuum, I will say electrovacuum, but this example I'm giving here is just pure PR. They all come from a common framework, which is the reduction of the gravitational action along a given symmetry. So to understand this, let us consider 4D vacuum GR, given by the Einstein field reaction. And let us be concrete and say that we are gonna reduce our action along a time-killing vector psi equal dt that is providing me with a line element in certain adapted coordinates. So my aim is to take this action and reduce it along my timeline killing symmetry. This is basically mathematically equivalent to reduce a Lagrange plane GR from dimension 4 to dimension 3. In my metric, F is basically my gravitational potential, which is the norm of the killing vector. Omega is the twist of this killing vector. Basically, is related with rotation, if the initial space-time has rotation, along which I am reducing. And the remaining metric, the 3D metric, here by this metric I call HAJ. So if you reduce, what do you find? You find that you have GR in the rich scalar, or GR in 3 dimensions. You have one scalar field that is related with my linear gravitational potential, and then you get this term that looks like a Dirac-Maxwell term, usually coming from my Kaluza-Klein theory, right? But the crucial fact is that in 3D, all these vectors can be dualized into scalars. So actually, this system, via dualization of the scalars, is nothing else than 3D gravity coupled to a couple of 2 scalars that here I'm calling U and sigma. This is a typo, it should be U. And this is nice because then 3D gravity can be written as a sigma model. Can be written as 3-dimensional gravity with a sigma model, where the symmetry of the sigma model is capital JAD, simply collect my 2 scalars. Why is this relevant? Because actually, the target metric of this sigma model expressed on symmetries. In the case of GR, when I have just vacuum, the symmetry of this target metric is given by this coset. It's basically the symmetry SL2R, where you coset out the redundancies of the transformations that do not give me non-trivial solutions, right? This symmetry is known as Ehlers and is known to mix gravitational and potential and twist. So basically, I can start with a solution that has no twist. I can apply my Ehlers symmetry in this sigma model, and because of that, I can get a solution that now has twist. The type of twist that this symmetry includes is very well known, and it's actually the NAND charge. So I can take Schwarzschild, for example, reduce my theory, apply the transformation, and then I will get at the end of the day my Schwarzschild NAND solution. Now, if I, as a holistic picture, then let me just summarize. So basically, you have 4DGR that contains a sigma model with a hidden symmetry, which is my Ehlers global symmetry over here, that only emerged after reduction to 3D and dualizations of vectors into scalars. And at the end of the day, these scalars, which are coordinates on the coset space, provide new solutions to the same field equations. So this is the way this hidden symmetry arises in GR. If you go to electrovacuum now, the group of symmetries is a bit larger, is given by this guy over here, and now I have 4 scalars, which are my initial gravitational potential, my twist, dualized scalar, and 2 scalars that are related now with the electromagnetic fields, the electric field and the dualized magnetic field that is also dualized into a scalar intervention field. And what is happening there is that I do not only have Ehlers transformation, but I have another symmetry, another transformation, that is part of this symmetry loop, which is called Harrison. And that has an interesting effect, which is provides electromagnetic configuration coming from gravitational degrees of freedom. So I can have a vacuum solution, and because of the symmetry, I can construct now an electrovacuum. For example, I can take Schwarzschild and end up with Rydell. I can take here and end up with Newton. So these are basically all the symmetries and the techniques that are behind the development of all of these fancy solutions that are contained in the Lemaskier metric, and that are the ones that we are going to be using to construct new solutions. Yes.
So, but we couldn't generate the curve parameter, we could generate the nut parameter.
Exactly.
The curve parameter.
I will say something about it soon. So, at this point, how do I sort this? Okay, yes. So to generate here, you need more integrability. And actually, what we have been doing here is just to reduce Einstein theory along one Killing vector, so basically one symmetry. You disclose this hidden liquid symmetries, fantastic. But if you want to go and disclose the full integrability of GR, integrability in the sense of the existence of a lax pair that allows me to use inverse scattering method and so on, then you need to compactify the theory and not 2 symmetries. When you do that, you move from 4D to 2D, and when you have 2D dimensional system, then you have the entire, you have at your hand the entire machinery of integrability in GR, and then you can produce Kerr out of Minkowski. But at this point, so also everything is pretty. Sorry, this moved a lot because of the. So let me just go a bit faster. Now let us do precisely what you are asking. Let us reduce along 2 Killing vectors. Let us say that my initial space-time is not going to be only stationary, but it will be also axisymmetric, and let us reduce the theory. When you do that, you reduce GR. Then this is very interesting because allow us to work with these symmetries that already exist by reducing along 1 Killing vector, but allow us to work with them in a very algebraic manner. And this is what I wanted to show you because this is what we do to find our new solution. So the stationary and axisymmetric space-time for D are basically characterized by the action of this group, R times SO2, under which the space-time metric remains invariant, obviously, so translations on time, rotations around an axis of symmetry. If the orbit, and this is very important because if this doesn't happen, the sigma model production doesn't work. If the orbits of this group R times SO2, which are defined as so-called surfaces of transitivity, are everywhere orthogonal to a family of hypersurfaces defined by the remaining non-Killing coordinates, which are called meridional surfaces, then the space-time is also said to be circular. It's not only axisymmetric and stationary, but it's also circular. And the action of this group is said to be orthogonally transitive. What this implies that the time-killing part of the metric and the non-killing part of the metric, they decouple. So you can write your metric like in a block diagonal form. And the most general line element that satisfies these conditions, that are circular, stationary, and axisymmetric, is a so-called bi-Levis-Pavavetro space-time, and it's double with rotating or magnetic counterpart. So basically, this is the standard bi-Levis-Pavavetro line element, which has a cosine that simply arises by double with rotating the time coordinate with the azimuthal coordinate and gives space for this second line element over here. These are the two most general line elements with these properties. And they are nice. Why? Because then you can reduce GR along them. And when you do that, you find that you can write Einstein equations in the so-called Ernst form. Ernst form is not the Ernst form or Ernst equations is nothing else than the 2D reduced Einstein equations that are written in terms of a complex potential, that is epsilon, that in the case where the theory has been reduced along the double with rotated one, the magnetic one. I'm using the magnetic one because it's going to be useful for our solutions. Takes this form, and where the integrability conditions that were relating the dualizing of the scalar, of the twist into a scalar is given by this so-called twist equations. And what is nice of writing Einstein equations in this form? Well, two. First, two nice features. First, that the equation acquires this vectorial form, with all of these vectorial quantities are defined over a flat space-time with cylindrical coordinate. So it's more easy to handle integrating this Ernst equation than directly Einstein equations in 4D, for example, because of this. But more importantly, this equation over here, the Ernst equations, disclose the symmetries I showed you before, the Ehlers and the Harrison groups, in a very nice way. It basically allows us to disclose these Lie point symmetries and to work with them algebraically. So basically, saying, look, if you have a seed, epsilon 0 and phi 0, in the case of electrovacuum, this is my initial Ernst potential, the gravitational one, and this is the electromagnetic one. The action of this group I showed you before, the Lie point symmetry, follows as here. These are nothing else than gauge transformations, so not relevant. This one is the classic electromagnetic duality invariance of 4D Maxwell theory. But these two are Ehlers and Harrison. This is the one that allows me to produce not charge in one case, and this is the one that allows me to produce electromagnetic fields out of vacuum. Okay? So this is why it's so nice to work directly with the Ernst formalism and to go into 2D reduction and not to stay only at 3D. Although working in 2D constrains us a little bit because I have reduced along one extra Killing vector. So my initial line element requires more symmetry to be used. And we will see in the second part of the talk that this is precisely what we are avoiding to be able to construct time-dependent solutions. Because if I would have started with a biparallel answer, of course, my metric cannot be time-dependent, because it must be a stationary analysis metric. So let me tell you quickly about the effect of these symmetries. So when we apply Ehlers-Harrison on a sealed space-time that is written in the electric Bavelian form, the resulting space-time must be asymptotically flat, because the initial electric Bavelian space-time is asymptotically flat. What that means, that the effect of the transformation, Ehlers-Harrison, should respect this asymptote. So that's why when I generate twists with Ehlers, I am adding not charge, which basically maintain locally the asymptotic flatness of my solution. And it's the same reason, and the same reason is behind why Harrison transformations include on my space-time monopolic charges, and either electric or a magnetic monopole, because these two, they respect the asymptotic symmetry. Very far, the Coulomb potential goes to zero. However, when I start with the magnetic biparallel space-time, this space-time is not asymptotically flat. It's actually something called asymptotically Levi-Civita. Levi-Civita space-time is a space-time of an infinite line with mass per unit length sigma that respect cylindrical symmetry. So now when I apply transformations of Ehlers or Harrison kind on the magnetic version of the Bavelian, I need to be in agreement with this weird asymptotical infinity, the asymptotic Levi-Civita asymptotic. That's why now Ehlers cannot include not charge in the space-time, and Harrison cannot include monopolic charges, but they do include background properties to space-time. In the case of Ehlers, is the so-called swirling background that many of you have been working on it, and in the case of Harrison, is melding monoelectromagnetic fields. Basically, they spread either this NAT parameter all over the space, giving us swirling, or they spread electromagnetic fields all over the space-time, giving us, for example, what the melding solution is. Any question?
So when you apply this Levi-Civita, so is it really backwards there the source? So
There is a source, which is the mass that is a singular axis that actually is the mass. Yeah. The thing is that you don't have a TB Newton, like pretty much what is happening with the solution you told me. Okay, so but there is one less explored symmetry, and this is related with our work. So far I told you well-known things that has nothing to do with our own novel results. There is a less explored symmetry that is a combination of the video symmetry somehow, and it's called the inversion symmetry. And the inversion symmetry is a combination of a gauge gravitational transformation, a bi-rescaling, rescaling, and an Eller symmetry. Okay, and what it does is that takes my gravitational Earth potential and my electromagnetic Earth potential and invert them in this way. So basically, the gravitational one goes as 1 over the C, and the electromagnetic one gets divided by the gravitational one. And given a vacuum C, you can see that the effect on the metric is very simple. It takes my original gravitational potential, F0, and via this formula provides me a new one, and change in a very similar way the twist of the space-time. Let's remind that this is not directly the rotation. This is something I need to use in my twist equation to recover the actual rotation. And nobody explored this, and was surprising for us, in the stationary case. The only solutions that were known were solutions that were found by applying inversion into static space-time. For example, Church. If you take this transformation into Churchill, you get something which is called the Churchill-Levi-Civita black hole. But nobody did in the stationary case. And we did, and we found a new rotating space-time in vacuum that we dubbed the Levi-Civita space-time. I'm not going to go into all the details of the geometry and causal structure just for the sake of concreteness, but it's basically we have taken a Kerr black hole, which is a rotating solution in vacuum, and we have inverted it and found a new solution that now not lives on top of Minkowski, but lives on top of this Levi-Civita vacuum. And that's why it's a valid alternative to solutions coming from the type B class of the Belansky, because now the space-time on top of which the source exists is not conformally flat anymore, but it's Levi-Civita. So some comments are in order. For this metric, is free of closed-like curves, is free of conical singularities, has no Minster strings, has an asymptotic form that is a bit obviously exotic because goes as a rotating Levi-Civita at infinity. People might think, but this is like swirling rotation. It's very similar, but it's not precisely swirling. And more strikingly, and let me just go fast on all of these details, the solution is fully regular from the point of view of curvature invariance. So I'm saying this is a very nice feature when we found it, but now, due to recent discussions, we believe that maybe actually the solution might have a singularity, but not of the curvature type, and it might be geodesically incomplete, something nobody ever so something that nobody checked so far. But anyway, the logic behind the solution and the type of rotation it has is the following. So you have a Levi-Civita spacetime. If I put a mass, I have Schwarzschild Levi-Civita. Nothing weird, I go to infinity, I have Levi-Civita asymptotic. Now let me put Kerr there. What is Kerr doing on this asymptotic? He's dragging a Levi-Civita spacetime. So when I go very far, I'm not expecting this dragging to be zero. Like if I try to drag Minkowski, right? Because now I have a non-trivial asymptotic infinity, and this dragging produces certain rotation very far. This rotation is this kind of swirling rotation that we found on our metric, basically this one. But it's not swirling because if you kill the mass, kill the rotation everywhere, just like in Kerr. Instead, in swirling spacetimes, when you kill the mass, the spacetime still rotates because it's a background rotation. So this is why we believe this is not a
Question. So in the swirling, you also have this sort of counter rotating north-south, but here
is different.
Yeah, it's different, right?
Yeah. So this is why we believe it's actually novel by itself, although it might have this underside feature that we still need to check. So this is one large family of solutions we have found that is kind of in parallel to the Blavatsky-Iliansky family. Why is not inside? Because our solutions are algebraically general are not type D anymore. And this is related with the fact that they exist on a different background, which is not conformally flat, but Levi-Civita now. And now let me tell you about the second family of solutions, something that was happening very recently, on which we have also contributed, and is related with some new vacuum solutions that are coming from the so-called Bertozzi-Robinson black holes. So recently, a new family of black holes on top of Bertozzi-Robinson electromagnetic backgrounds have been proposed. Now, this is important because the Bertozzi-Robinson electromagnetic background is conformally flat. So if I put a source on top, I might have something new that is type D. And actually, this is what they found. They found a new Schwarzschild black hole that is on top of a Bertozzi-Robinson black hole. This is the metric over here, and it represents Schwarzschild on top of this background. This Bertozzi-Robinson background is a very well-known geometry that has a nice property that is the direct product of two spacetime of constant curvature. It's basically ADS2 times 2. And it represents an electromagnetic background that is all over the spacetime, that has a constant value, and produces a constant curvature spacetime, which is conformally flat. They were able to put a Schwarzschild on top. Okay? Now, what if we apply our inversion symmetry to this solution? What we found is that applying the...
So did you say that this was type D?
It's type D. Actually, it's type D when you put Kerr inside.
I see.
Yeah.
So was there some uniqueness for the Blavatsky-Iliansky?
Very good. Why this is circumventing the Blavatsky-Iliansky theorem is because the electromagnetic field that sources this Bertozzi-Robinson background is not aligned with the two principal null directions of the type D spacetime. And the Blavatsky-Iliansky metric is the most general type D electrovacuum solution when the electromagnetic configuration is aligned with the two principal null directions of the spacetime. In this case, this is not aligned. And people were exploring non-aligned solutions in the context of Robinson-Trautmann and many others, Carbenati and these people. And what they found now was, okay, let us go further and let us try with Kerr in a context of black hole physics instead of radiative solutions. So let us apply inversion. And what we found applying inversion was something very interesting, was that the new electromagnetic potential goes to a constant when inverted it. Why? Because phi 0 and epsilon 0 were proportional for this metric. What this implies is that by applying the transformation, I can completely extract the electromagnetic background, but I still get a non-trivial solution for the metric, a solution in which there is a trace of this original electromagnetic field. So I simply disappear the electromagnetic configuration, but the imprint of the electromagnetic configuration in the metric doesn't disappear. And this is a new vacuum solution, therefore. That, unfortunately, because we have applied this symmetry, is type D and not type 1. Sorry, type 1 and not type D. Okay? And this is very nice, and this represents new vacuum solutions for the equations. Unfortunately, I'm not going through all the technical details of the geometry, but first, the vacuum nature has been a bit put into a trial, because although there are no unbound curvature invariants, it's okay from the curvature invariance point of view. It seems that it's geodesically incomplete, and that this geodesic incompleteness is related with the presence of a source that wasn't seen in the linear coordinates we used to find the solution. So this is unfortunately something we need to rewrite somehow. But anyway, it's a new vacuum solution. And second, there is an issue that has been also recently discussed, is that there are certain people that insist that all the solutions that has been found via the inversion symmetry, our KR-Levichvita, the new one, inverted Berthollet Robinson, they all belong to the Kerr-Swirling family that was found by Astorino and company before. Well, actually, the original Swirling solution was found 7 years prior to the paper of Astorino by the father of Witten, Louis Witten, in a paper in 2015, where he just wrote the expression, but he never called it Swirling, he didn't say anything about it, and this is the original paper. However, it is fair to say that Astorino was the first analyzing the properties of the solution. So Astorino claimed that actually the Kerr-Swirling family, via some singular limits, will provide all these solutions given by inversion. This is locally true. There is certain limit that connects certain geometries. However, from a global point of view, this is completely different. The solutions you get when you take this singular limit are either solutions with conical singularities or domain walls, but they do not represent black holes with a compact horizon. So it's a matter of discussion. And well, to understand actually why the inversion gives non-trivial new solutions, we need to dig into the real shape of this transformation, and this is something we are going to write about soon. So basically, this concludes the first part of the talk, where we have understood how to use Lipman symmetries and how with them to still be able to find certain vacuum solutions, either they are not probably the most astrophysically relevant, but from an exact solution point of view, they are very nice, they have interesting properties, and tell us that still we can use this technique to find new solutions in vacuum, which is very surprising after knowing the book of Stefani and company, and the fact that we have already 100 and something years of general relativity on our way back. So now let me talk about the second part of this talk, which is related with constructing dynamical black holes in 4D, and how these somehow connect with all this machinery of Lipman symmetries I showed you before. So, some motivation. Why we must deal with dynamical black hole solutions in the first case? Well, realistic black holes, so namely astrophysical black holes, are inherently dynamical because they are formed, fed, perturbed, and they interact within a dynamical universe, within a cosmology that is actually expanding in an accelerating way, right? They are formed via gravitational collapse, which is a dynamical setting, so even the given horizon itself is a dynamical outcome and not a stationary condition that I have imposed from the beginning when I studied, black holes in the classical setting of stationary spacetimes. Moreover, stationary solutions, they assume eternal existence and equilibrium. No matter flux goes across the horizon, there is no gravitational radiation, and my entire spacetime has a time-killing symmetry everywhere. That means I have a very isolated source, and nothing is changing, not on the source, not outside. This is very restricting from a astrophysical point of view. We know actually that astrophysical black holes, they accrete matter, they merge, they emit gravitational waves, and more importantly, they exist in a dynamical background where there is no time-killing symmetry. So it is actually tempting to try to apply all these solution generation techniques to try to describe black holes that now are in a dynamic set. And there are a few knowledge models. The first one is from the 30s. It's known as the McVitie spacetime, which is basically a Churchill black hole that is written in isotropic coordinates where there is this time dependency in the metric, which is actually an arbitrary function. So this is a solution of certain theory with a certain fluid for which there is an arbitrary function. And defining the time dependency of the metric implies defining the type of matter I have in my universe that give me the chance to construct this solution. A second example of this kind is also called a Gunther spacetime, which is again the same. I'm taking Churchill multiplied by a time-dependent conformal factor and finding an ad hoc fluid that again satisfies my Einstein equations and that leave one free functions to play with and to describe different models. These, of course, are both asymptotically Riemann-Lemaître-Robinson-Walker geometries. When I go very far, this guy goes to Minkowski, and I get conformal spacetime. When this guy goes very far, also I get Riemann-Robinson-Walker. There are other geometries of the same kind, the so-called Bagirian solutions, either Churchill or Kerr, where basically it's a vacuum solution that to which the mass is upgraded to depend on time or to an coordinate. And these are solution sources again via fluid. So most of, if not all, solutions in the literature in the concept of dynamical black holes, they go with the same logic. They take a metric, they make it time dependent somehow, either upgrading the mass or multiplying by a conformal factor, and you find the fluid that will make this to be an exact solution. So basically, I am subdetermining my system. Now I have more free functions than equations. And this is how it is. But there is one model in the literature for which this doesn't happen. It's called the Fonarer scheme, or we call it the Fonarer scheme, but it's because Fonarer found this solution. And he was able to take a source and to embed it in a cosmological spacetime without going into the use of fluids and by actually having the same number of equations than unknown functions. How does this work? And this is basically what we have been working lately. Fonarer scheme is telling you the following. So basically, take a given spherically symmetric static solution of the Einstein scalar theory. Einstein with a minimally coupled scalar. No potential, no mass, no nothing. Take a solution there. Then a time-dependent extension for such a configuration is given by these expressions over here, where the metric of my initial seed is multiplied by a conformal factor again, and where my scalar, the original one, has been upgraded by a time-dependent profile that is proportional to such a conformal factor, and where the conformal factor is fixed by this expression over here. So there is nothing to be defined by hand. This is basically imposed by the field equations, and where now the solution solves Einstein minimally coupled theory, but upgraded with a potential. And this potential is also fixed and is not integrated out. This from the beginning in the action, and it corresponds to this Liouville time potential you see here. And this new configuration is a solution of this theory modulo the following constraints between the parameters that here I have called psi1, psi2, and the ones related with the potential, satisfy this relation. Okay, it sounds very like abstract like that, and let me show you why this works and from where it's coming from. Basically, to understand it better, let us dissect the role of the scalar. So first of all, the scalar should be such that produce cosmological behavior very fast, right? So let us have no source. Can I produce Riemann-Lemaître-Robinson-Walker with a simple scalar in this theory? Yes. If I take minimally coupled Einstein with a minimally coupled scalar field, I can always find a Riemann-Lemaître-Robinson-Walker background for this scalar profile. It's very easy. This is conformally flat, you have everything going well. But now, the same scalar should be able to produce the original Einstein scalar solution, which is static. So my scalar should be able to exist along or around a compact source, right? And how is this possible? Well, we know that by brute force, we know that there are solutions of this kind, the Fisher-Yanis-Newman-Winiger solution, and generalizations thereof. But why this work? Why do these solutions actually exist? Because it's not a coincidence that you can integrate equations in that system. And they exist because of a sigma model symmetry again, which is very interesting, which is the following. So consider now compactification of Einstein scalar theory along a stationary timeline killing vector. So I take my metric, no rotation at all. I will tell you why, not yet, but I will tell you. You compactify your theory. What do you get in 3 dimensions? You get Einstein in 3D, you get your original gravitational potential, and you get your original scalar that completely decouples in the compactification. And this is again a sigma model for 2 scalars, and it's a sigma model with a very simple target metric. It's basically 2-dimensional flat space-time. And here you have some symmetries. You have translations, chip symmetry for the scalar, but you also have rotations. By applying a rotation, you can always generate a scalar coming from gravitational potential. So basically, the simplest way to see this is in vacuum. Let's say I started with pure GR, so my initial phi was 0. I compactify, I get my sigma model, and I apply a rotation. Because of the rotation, now I can generate a phi prime, a scalar, even if my phi original was 0. And this is why I can take, for example, Churchill and put a scalar on top and generate the Fisher-Janis-Newman linear solution, which is this expression you see over here that I wrote just for completeness. Now, Faraday, what he did was by brute force, he understood, I can combine both profiles from the scalar. The one that very far will provide me with my Riemann-Lemaître over behavior, and the one that provides me with this Einstein scalar solution, and actually works. And you find this time-dependent black hole, which is a time-dependent generalization of the Fisher-Janis-Newman linear solution. So basically, here you have the Einstein scalar Fisher-Janis-Newman linear space-time, has been upgraded by this conformal factor. This is my original static profile for the scalar that has been upgraded to time-dependent scalar by this other piece of the profile, which is basically the same than the conformal factor. But why the merging of these 2 things works? Because we understand why each piece works, but why both actually work. So to do that, we wrote a paper, to say that, we wrote a paper where we, first of all, asked ourselves if there was any major restriction to remain in spherical symmetry. Can we go beyond spherical symmetry? Can we go axisymmetry? Or can we go to consider rotation? This was the first thing we wanted to tackle in the spectrum. And the second one was to understand if there is any reason behind of this mechanism working, because it's not a coincidence, as we have seen all along this talk, discussing liquid symmetry and so on. All these solutions, they don't exist because you are lucky enough to solve the field equation. There is something going on behind, right? The liquid symmetry or so on. And to do that, it is convenient to generalize the theorem. It's very convenient to actually take this liquid symmetry that allows you to scalarize somehow a given solution and to write it in a metric formalism, because it's very ugly to go compactify, come back, right? Actually, there is a metric description of the same symmetry, so basically same equivalent symmetry but written in metric form, and this was given long ago by Buchla. It's called the Buchla theorem. And Buchla theorem tells you, look, take a static metric that has one symmetry, so one killing vector, and don't tell me if the scaling vector is time-like, space-like, or nothing. Just write the metric adapted to that killing vector. So this ignorable coordinate will be called A. Okay? Write your metric like this. And assume that it's not only an ignorable coordinate, but there are no cross terms. So basically, the twist-free condition I told you before. If you take a vacuum solution with a symmetry of this form, you can always write a solution with a minimally coupled scalar field around that will take this form, where now the new profile goes as the logarithm of this metric function. Here, I'm not saying if A is a time coordinate or the simultaneous coordinate, and this is completely generic. And now then it's super easy to always combine this with Faraday. But we know, upgrade your metric with a conformal factor and do the same with the scalar, and then the remaining parameter will satisfy some constraints, right? So we have basically shown there that you can always have FONAREF to take a vacuum solution with certain symmetry and to upgrade it to a solution that now lost the symmetry by having dependence on this coordinate. So you can take a static solution and transform it into a dynamical solution, or you can take a solution with axial symmetry and transform it into a solution that depends on the angle phi, or cylindrically, or any killing coordinate you wanted to use from the beginning. And this is what we did there, and this implies something very simple, that the spherical symmetry was never part of the game, and actually you can start with axis symmetric configurations. So I can start with Seybold-Bordkis family of solutions, transform them into time-dependent Seybold-Bordkis, just to give you an example. Now, an important comment that I think I have like 10 minutes. Yeah? Okay, thank you. So, important comment is that the solutions exist, or FONAREF-like solutions exist, even if there is no Liouville potential in the network. So, let me just spend a minute discussing this. Let me show you the action. So my action has this potential, and this potential allows me to find my FONAREF state. But notice that if I don't want to have a potential, if I keep this zero, these constraints can be still satisfied, but the only thing I have to do is to fix the scalar charge here, because this guy will be zero. So I need to fix my scalar charge beta over here. All of these constraints are going to be satisfied, and I still have solution with no potential. That solution was found month or 2 months before actually FONAREF put his paper. It's called the Hussain-Martinez-Núñez solution. And I am telling you this because it's going to be very relevant for us, because the next step I'm going to show is that all these FONAREF solutions can be magnetized. And now we can have black holes on top of a cosmological universe that also contains a time-dependent electromagnetic exterior field. And as I told you before, these Liouville symmetries will work in Einstein-Maxwell with no potential terms. So what do I need is a seat without the potential. So that's why it's important we don't have the potential already. Okay, so now that I have said that, let me quickly tell you why this works. And actually, if you know about Kaluza-Klein, you know that the action of FONAREF is precisely the compactification from 5D to 4D of GR with cosmological constant. So basically, this told us, okay, these solutions of FONAREF, they must exist because they correspond to compactification coming from 5D. And how do we prove that? Well, we do the opposite. We write our solutions in 4D, and we try to uplift them to 5D. And we found something very interesting. We found that the solutions of FONAREF, here I fix the coupling to certain values and not in the most general case, have this shape that actually can be written in this very suggestive form. This looks like an Euclidean Schwarzschild that has been transformed into an inhomogeneous black string where the work factor depends on time now. And if you simply perform a double Wick rotation of this 5D line element, what you get is the classic Schwarzschild, the classic type of inhomogeneous black string you find in ABS. So it is known that if I take Schwarzschild and I include one extra coordinate, let's say dx squared, I can uplift this to d equal 5 for free. It's always solution. But what if I have cosmological constant? What if I have Schwarzschild in ds in dimension 4? Then I cannot simply put dx squared and this be a solution in 5D. What I have to do is to put a work factor on top of my black hole plus dx squared to go to 5D. And this is valid for the entire GR family. So I can take all Blavatsky here, do this, and this will be solution. Now, our uplifted solutions are basically the double Wick rotation of this one. So if someone would have liked to discover FONAREF, not by brute force, that FONAREF did, they should have asked themselves, okay, can I take a homogeneous black string and double Wick rotate it? What if I compactify to 4D? They would have found FONAREF, but obviously that was super exotic way of thinking, and nobody did. But this is the reason why the FONAREF actually works. Because if you see, f of t times this guy will provide me with my scalar here. And this is precisely the type of profile the scalar has. Logarithm of this guy plus logarithm of my conformal factor. So that's why it's that scalar and those two profiles that can be combined and not any other scalar. Okay, and in the last 5 minutes I will try to tell you a bit about generalizing this Faraday, but now in the context of magnetic fields. That might be also astrophysically relevant, although it wasn't our aim, to be honest. So now there is something interesting. All the symmetries of the sigma model, they decouple when I have a scalar. So for example, if I compactify Einstein, I get Eller's group of hidden symmetries. If I compactify Einstein-Maxwell, I get the extended SU21 symmetry. What if I put a scalar in the action also? What I get is the same symmetry times direct product of this guy. This implies that I can always use my symmetries and the scalar field is not affected at all. So all my Ehlers, all my Harrison, all my inversions, all my Leeds-Pauli symmetries also work when I have a minimally coupled scalar. Now that the minimally coupled scalar is the main ingredient behind Von F, can I magnetize or apply Ehlers into my Von F scheme? And the answer is yes, and you can find magnetized black holes. And actually, let me show you very fast. This is the magnetized version of the Von F black hole over here. Basically, this is a magnetized Fisher-Janet-Newman-Winniger black hole that has been embedded in a dynamical spacetime. And although there are many things I would like to tell you about this geometry, especially in the master case that provides a time-dependent melting boundary spacetime that nobody found before, I will skip these details because I would like to show you how to analyze the causal structure of these solutions, which is the most important part. Because these solutions belong to minimally coupleizing theory, they all have naked singularities, even in the time-dependent counterpart. The question is, now that I have a dynamical setting, can a dynamical horizon cover this singularity? It's a very important answer to a very important question to answer, right? So to understand actually the causal structure of these black holes that are now dynamical, because it's already clear that the static one, they are naked singularities. And actually you can do that, and to do that, and here probably I will be more, I will go faster, don't screw up with the lunch. To do that, you need to study dynamical horizons, dynamical black hole horizons. And how to define that, what is the main concept behind a dynamical horizon is to find a trapped surface for your photons. Because we know that we have no clean symmetry, so I don't have clean horizon concept at hand to define where the horizon is. The only thing I can do is, can I find a trapped surface for outgoing photons, such that this trapped surface might define what my dynamical horizon will be? And this is done using the high-word formalism. So basically what you need to do is to have an foliation of your space-time to find a trapped surface that is defined by the condition of outgoing zero expansion, of negative ingoing zero expansion. And if you want this trapped surface to represent a black hole, you will ask that the derivative of this expansion satisfy this condition. Now, in a spherical symmetry, we already have certain degree of ambiguity because there are many null foliations. I can always find null tetrads. Which of them will give me a physically meaningful trapped surface that might represent the horizon? This is not that easy. However, in a spherical symmetry, because there is a lot of symmetry, this can be always done thanks to the so-called Kodama vector. The Kodama vector has a property, and the property is that its norm is proportional to the expansion that defines my trapped surface. So every time I have a spherical symmetric space-time, although it's dynamic, I compute the Kodama. I see where the norm of the Kodama goes to zero. This immediately allows me to find my trapped surface. Problem solved. I can proceed with the causal structure of my dynamical spherical symmetric space-time. However, our solutions are axisymmetric, and I don't have the Kodama anymore if I have axisymmetry. But we have another vector which is called the mean-Kirchhoff vector that is used a lot in numerical relativity to find trapped surface of highly complex dynamical spacetimes. And this is a vector that tells me how a 2D surface is embedding on a 4D spacetime. Basically, how I embed my trapezoid surface. And this vector that is defined by these formulas over here, I will go a bit more faster, has the same property than the Godal. The norm of the mean curvature vector is always proportional to the products of expansions. So when I find a zero of the norm of the mean curvature vector now in the axis symmetric setting, I can always find a trapezoid surface. But unfortunately, and I will just comment on this, yeah, I have solved my problem. Now I have a vector to find my trapezoid surface, but this vector is foliation embedding dependent. I can have a 2D surface embedded in a 4D surface in many ways. So now, which is the physically meaningful way? This is a problem, especially if you have axis symmetry, and this is where numerical relativity is very important because you need to define a numerical embedding and solve the system numerically. But there are specific cases in which the axis symmetry is compatible with the simplest of the embeddings you can make, which is the embedding TR equal constant, the one you will use in spherical symmetry. And our magnetized solutions are precisely that kind, because the horizon of the magnetized solutions, if you remind Schwarzschild-Melvin, does not change because of the axis symmetry of the solution. It simply gets distorted. Well, you can do that. You can proceed with the entire analysis in this case of the mean curvature vector, and you find a very interesting dynamic for the horizon. And with this, I'm going to close. Basically, you find what is so-called the S curve. The horizon of a solution like our magnetized is the following. From the Big Bang initial singularity to a critical point here that is called T1, there is one cosmological horizon that expands over time. Eventually, at this first critical point, two another horizons are created. One that is cosmological, that expands towards infinity again, and another that is a black hole outer travel horizon that contrasts until a point, another critical point T2, where it actually merged with the original cosmological horizon, and eventually everything after T2 is only dominated by the expansion of the universe, and only one cosmological horizon pervades. So basically, our naked singularity is initially, our singularity is naked, covering only with the initial cosmological horizon. Eventually, two horizons more are created, another cosmological and a black hole horizon that covers the singularity now for a period of time, until which, again, two horizons disappear and only the cosmological one pervades, and the solution is again naked. So this type of black holes that I showed you, this dynamic black holes with a source, are basically solutions that can be interpreted as a naked singularity whose ability to cloak light is temporary. It's a sort of classical Hawking evaporation mechanism, because you have the horizon. Yeah, it's a very, I'm crossing the line with the analogy, but the point is that for a while you can cloak the singularity, and then the expansion is so strong, and then you get only cosmological horizon, and the contracted horizon disappears. And all of this can be studied by understanding the mean curvature vector. And this is very interesting. And this is the only system where these solutions can be actually constructed exactly, where you can put actually a source and a cosmological space-time. And this is very non-trivial, without need of any fluid. Now, for all of them, you always get, for the ones for which there is an analytic study of the causal structure, all of them follow the S-curve. So now, to close, our Fonaret scheme might be very relevant. Why? Because let's say I have an axis symmetric solution now, for which I cannot simply apply the trivial embedding I used to find this solution. I used to study this solution. Then I will have to go numerically to define the horizon structure. So it might be the case that actually in more general axis symmetric settings, for example, at an independency with Borges, the horizon structure will be completely different than the S-curve. And maybe we can analyze solutions for which the history of the cloaking of the singularity is completely different, and this would be very nice. And yeah, and would be also nice to understand if all the solutions can be interpreted as primordial objects, if they exist actually in a cosmology that accelerate, that expand, and it accelerates. Unfortunately, the ones we have here, they exist in cosmologies that are either contracting or decelerating. So they can be mostly interpreted as collapsing solutions more than primordial object. That would be very nice to all the research that has been going on regarding primordial black holes. Okay, so I think I will close that. I will just leave this 5 point to explore. That is basically what I said. It would be very nice to go beyond all these solutions and to try to understand the thermodynamics of all of these time-dependent spacetimes, because we know the mean Kilroth vector has been used to define quasi-local energy in this context. There are a lot of works of Ashtekar, Highmore, and company using it, and yeah, I think I will close that. Thank you very much.
Thanks a lot for the very complete talk. So we have time for a few questions.
Yes,
this one.
So first of all, thank you for your talk. This is regarding the first part of your talk. What kind of leap point symmetries would you get if you integrate the Einstein-Field equations along only space-like Killing vector fields?
Okay. Yeah. So basically, in that case, you get the magnetic versions I was showing in that very second part. So compactifying along dD or d5, let's say, for example, is equivalent to start using the symmetries either with the electric momentum answer or with the magnetic one. So the compactification along space-line Killing vectors is basically the one that give you background time of fields outside. Obviously, here I show you a stationary and axisymmetric spacetimes, but the reduction from 4D to 2D to write the symmetries as I showed you before works for any couple of commuting Killing vectors. So you might have, for example, any G2 group of symmetries, the spacetime of the Einstein-Rosen wave family, for example, they have cylindrical symmetry and axisymmetry. Then you have two space-like Killing vectors. You can do the same reduction and apply the symmetry set. Anyway.
Would you use that, for example, with the Bailey spacetime, which is spherically symmetric?
With Bailey?
Bailey spacetime, yeah.
Like the one I showed you here?
Yeah.
The thing is that there you have the fluid, and the fluid will break the symmetry. And so far, the only two fields that do not break the D-point symmetry structure, but there are more, but okay, it's more tricky to say, but minimally double scalars. Maxwell and Einstein-Dirac Maxwell theories that are coming from compactifications. All of these somehow related with higher dimensional compactifications. They retain a non-trivial sigma model symmetry. But if you go with your favorite scalar or fluid, this doesn't work. GR is very restrictive.
In the last of the plots that you showed, so you showed this situation when the formation of black horizon is accompanied by the formation of a cosmological horizon.
Yes.
So how general is that? Can we expect that in all cosmologies something like that should happen, or how is it? Because I have difficult to imagine how is that, no? Because at the beginning, both the cosmological horizon and the black hole horizon have the same size.
Yeah, well, this is a type of curve that appears precisely in this setup in which you have the compact source there on top. So it happens in the papers of Fonadev and other solutions that Castor and Trasher found long ago. And apparently, in my opinion, it's related with the fact that we have this particular type of source on top. And I don't know if there are other cosmologies for which this is different. For example, in Baillia, at the static case, I guess it's easy to find the horizon structure. I don't know the shape, so I cannot answer directly your question. That one is asymptotically flat, so I'm not expecting a cosmological horizon. Baillia, nobody knows, apparently, because it's very hard to find it numerically. Now, I think there's still research going on into how to find the horizon structure, the apparent horizon structure of Baillia, because it's axisymmetric and you need to use the Kilroth vector to work the numeric. Is very difficult. Now, the one that I know that have source on Freeman, Royce, or Walker are these ones, and they have this. They show this curve. We don't know the answer precisely why the curve has this form. It for me it's logic that very far the cosmology, because you are far of the source, the cosmology prevails, right? So that's why very far you have this one cosmological horizon, and eventually you will have an Naked singularity. Now, how the source best for earlier times, the horizon structure is not something that I really know why. To be honest.
Thank you.
Let me just ask if there are questions online. Apparently not. More questions here?
Well, can I say, so when you give that list of kind of black space that dynamical with in the cosmological backgrounds, I was thinking about the Castor Trashel solution in which you have extremal Rasmussen in situ. That means you don't really have a fluid also because it's well, it's a cosmological constant. Maybe you can think about cosmological constant.
Yeah, but it's true. I was cutting a lot of the slides on this talk that was already long, and one of them was the relation of Trashel Castor.
Okay.
Yeah, and they found the same type of S-curve. So they also found that the black hole case corresponds to a contracting universe, which is the main issue behind this solution. I don't know if I explained myself well, but once you have this solution, it's very important to analyze, okay, in which type of cosmology they do exist. In the cosmology I observed, so I can tell these objects are primordial. I need a cosmology that accelerate and expand and accelerate. Unfortunately, when you have the source, always the black hole exists in something that is contracting in a decelerated way. And to get something that is in a cosmology that expands, it's always the white hole, actually. So this horizon here might be a black hole or a white hole. Sometimes, when this is expanding, actually, it's a white hole here. But it also expands less and less over time. So it's solving half of the problem. So Trashel and Castor, and I believe that one of those was the practice of our paper, actually, they already pointed out that this behavior will have a source.
But to have acceleration, you need a violation of the strong energy condition. Could this matter content?
I don't know. Yeah, I think so. Yeah, I don't remember now the explicit form of the energy conditions here, but certain violations are needed for this horizon to be dynamical, right? And this is precisely what is happening here. We have a dynamical space-like horizon instead of, for example, an isolated one. So I think here some violation of energy condition is actually going on.
I was thinking for a minimal coupled scale, you cannot get violations of the strong energy condition, if I remember.
If
So,
no,
you need some potential, right?
okay, yeah, well, in this case, we don't have the potential. In the end, for the left, you have.
You have, in that case, you have this,
The real one. Okay, there.
so
Maybe
maybe
that depends on the.
you could have some slow roll kind of condition, because then you have a sort of, it's an exponential potential. I don't know.
Yeah, I don't remember precisely now the condition of the flux on the horizon for these solutions. But we can discuss it later. In the isolated case, we know there's no flux. So there are certain non-energy conditions that are getting satisfied. In this one, in this case, I don't know. I don't remember. But yeah, it's a very important subject to try to now go to numerics and to having at hand the axisymmetric solutions to try to find a different horizon problem. To see if there is something more to squeeze from this model, which is the only one for which the metric can be written in a closed form. But I didn't say, but we can also, we'll probably soon upload into the archive the Swirling version of this. Because here I apply Harrison symmetry in a dynamical context. You can also apply Ehlers. And then you get something very, very, well, novel for us, exotic for many people, which is a source on a cosmological rotating background. This is highly non-trivial because rotating cosmologies, they do not have source on top. For example, Gaudi cosmologies are basically the cosmology that describe Kerr in between outer and interior horizons, right? You cross Kerr horizon, you have cosmology there. This cosmology has a sort of cross-term there, no? But you cannot interpret the mass of the linear Kerr there as the mass of a compact object living on this cosmology. The same way when you cross the horizon in Schwarzschild, you get this Tarkovsky SAR cosmology, and the mass became something different, right? Now we were able to put the mass on something that is cosmological and actually protects. We hope to show that soon.
Well,
Okay, I am extending too much. Thank you very much
we can continue the
for your
conversation
patience.
over lunch and the next few days since you're here. So let's thank you again.
Thank you very much.
Maybe you